This is Jim Hendershot, continuing with the lecture series number 30 on the performance calculations for brushless motors of the surface magnet type and the IPM type. We're going to discuss the performance calculations after, and based upon that, we've assumed that we've determined what the flux is per pole. We did that in the last series, and we assume that we've done the initial sizing has been done from as outlined based on the spec requirements in lecture number 4. We've already decided the pole and slot selection, the materials for the rotor, active magnetic materials, the diameter, the lengths, except based upon our air gap stress and electric magnetic loading. And the first thing to estimate is the voltage constant. And to make sure, this is a very important point with the design of PM machines. We've got to make sure that we start with the number of turns linking the flux that we have from the magnets that we selected in the last lecture. We have to make sure that our back EMF is less than the no-load speed because we need some voltage headroom to force current into the windings. It doesn't matter how you drive it, whether it's a sine drive or 6-step drive. The current, according to Ohm's law, the current flows in the circuit when we have enough voltage to get it there, and the back EMF is the opposite polarity to the DC rail voltage, so the back EMF subtracts from the voltage available for the inverter to force current in it. So I start with a typical allowance of 15 to 20% for voltage headroom. In other words, where I pick a back EMF constant, a CUSP, volts per 1,000 RPM, and I use the maximum RPM that I want to produce torque at, and I do a little simple arithmetic there to make sure that my rail voltage is 15 or 20% higher than what the back EMF voltage would be at the maximum RPM that I want to produce torque to. And then, after the flux per pole is estimated, then is when we want to calculate how many conductors we need for that flux linkage, and the number of conductors, Z, is divided by 2, and then divided again by the number of slots, and that gives you the turns per coil required. Each coil has 2 sides, and both sides link the flux of the magnets, so that's why we don't use T for turns per coil. We use Z, which is turns per coil times 2 times both sides, and the total turns in the machine is times the number of slots per phase. So the wire gauge is calculated to fit that number of turns in each slot area. We take the cross section of the wire and fit that into the slot area. Phase resistance and current densities are then easily calculated quite simply. So to calculate the number of turns required per coil, it depends on the supply voltage and the flux that we have and the diameter and length of the machine. So if we determined what the flux per pole was, that's B sub G from in the last tutorial, and then the number that equals the number of poles times flux divided by pi dl, and that's the surface area of the rotor. So to solve for, you solve for flux out of this equation, and then we know that the back EMF factor K sub E equals the phase voltage divided into the supply voltage. So the turns per phase is expressed by this formula here, and this form factor is usually assumed to be 1. And the winding factor, that's a winding distribution factor. That depends on how evenly or how perfectly that depends on the winding pitch actually. If the winding pitch is exactly in the center of the poles in the rotor, then the winding distribution factor is equal to 1. And the fundamental frequency is based upon the poles and the speed, just like in an induction machine. So, so we select the turns per coil to give a case of B a 15 to 20% left in the DC rail voltage at max speed we want to produce torque at. And as we said, Z is the number of turns per coil times 2 coil size times no number of coils. So the turns must be increased to overcome flux shrinkage reduction from skew or winding distribution factor. Or you could start off by ignoring both of those. So here's a conversion factor for volts seconds per radian to volts per 1,000 RPM. So for PM DC commutated machines with one phase on the rotor, the volt second per radian equals this relationship here. Total number of conductors, total number of active conductors, that takes care of the winding factor. P is the number of pole pairs, and phi is the air gap flux per pole, and this assumes one parallel path. If there's 2 parallel paths, you have a 2 in the denominator. 3 parallel paths, you have 3 in the denominator. So that's your basically relationship of the flux linkage of the turns and the flux. Turns in the stator, flux in the rotor, to determine what the K sub E is. And that can equal, for a DC commutated machine, that equals a torque constant as well. It's slightly different for brushless machines depending on how the back EMF wave shape looks like. So the commutation of these machines is, of course, very important. The BLDC or the permanent magnet synchronous are both identified as synchronous machines, but you could support an argument against this notion, and I base that discussion on the fact that AC machines are controlled by frequency, and if you want to call this a synchronous AC machine, then its frequency doesn't control the speed. Its speed's controlled by voltage, like a DC machine. But I will agree then that it's a self-synchronizing AC machine through a shaft angle sensors using Hall switches or encoders or resolvers, and that's required to commutate the phases properly. So it won't stall. It won't stall until it won't commutate the next phase until the rotor gets in the right place. If it was truly a synchronous AC machine, it would stall. If the inertia load was too high, it would stall before it got to the right position where the next phase should be energized. So what is the relationship between the shaft angle feedback data for commutation and the inverter currents that go to the stayed windings? These must be synchronized to the rotor poles through rotation and startup. If Hall switches you use, where are they located? Well, the placement of the Hall devices. Let's talk about where you place Hall devices or opto switches. Since PM brushless machines are bipolar driven, there are two control events for each phase that are required for electronic commutation. Now, each Hall device has 2 possible states. They're either high or low. So 3 phases require 2 control events per phase. That's a 6 of total control events. So 2 Hall devices with 2 states would only achieve the control of 4 events, and that's not enough because the 3-phase motor has to control 6 events. So that means we have to have 3 Hall devices. So 2 to the 3rd power is 8 events, but so 2 of the events are not used. So 4 control states are not enough, so we got to have 3 Hall devices. For a 2-phase motor, you could use 2 Hall devices because there's only 4 states that have to be controlled with a bipolar 2-phase, but that's not the case here. So for a balanced 3-phase winding, the slot number in the stator has got to be divisible by 3 with no remainder. So the phase set, the coil distribution of the phase windings must be 120 degrees mechanical apart. For even slot numbers, hulls are placed in line with slot openings. For odd numbers, hulls are placed in line with the two center. Okay, and they can be placed next to the stator as long as you don't have false triggering from the currents in the phase winding interns. That can be a problem. It's not a big problem, but it has been reported. So, but even if you're going to add a separate magnet to the shaft with a separate printed circuit board and the Hall device is mounted on the printed circuit board, since the coil distributions are 120 degrees apart, the three Hall switches have to be in factors of 120 degrees apart. We'll look at that in a minute. But with respect to where the hulls are placed with respect to the stator, they're placed in exactly the center of the slot openings if the slots are even numbered, and then centers of the teeth if the slots are odd numbered. So that means that here's a plot. For example, here's a plot of the back EMF of a motor for clockwise rotation, and then that's the top trace. The bottom trace is the TTL high-low output, the two-state output of the Hall switch. So that the alignment of those puts this positive side exactly at the zero crossings of the back EMF of the motor. So, but you will find that that occurs at the center of the slot opening for even slot numbers and the center of the tooth for odd slot numbers. So here's the counterclockwise rotation location, still centered over the zero crossings of the back EMF. But so you could physically align the Hall switches with respect to the vacuum EMF. You can do that on a little test stand with an oscilloscope and an adjustable a board for the Hall devices. The determination of how far the Hall switches are spaced apart is done by this relationship here. You divide the number of phases. You take the number of phases, divide it to 360, and that's the angle spacing of the Hall. It's electrical angle spacing of the Hall. Doesn't have to be the mechanical angle, the electrical angle. So like we said, if it's three phases, that's 120 degrees electrical Hall spacing. Now let's see. To get the Hall spacing in mechanical degrees, you divide let's see, I'm not. You can leave the Hall devices mounted in the same angle as the electrical angle, but if you want to make it smaller, you can use the complement of the electrical angles. In other words, you can take these you could take the center Hall device and call that the third one, and take the third one and put it in the spacing between the first two. That's the complement. So that would, but instead of identifying the Hall devices as 1, 2, 3 or UVW, they would be you'd have the Hall device could be 60 degrees apart instead of 120. That's what I'm trying to say. But instead of the Halls being UVW, they would be UWV, the way you'd connect them. So the third one becomes the second one. The last one becomes a middle one if you space them 60 mechanical degrees apart, because that's still 120 electric degrees apart if you redefine which phases they connect to. It's better to show that graphically than by words. Open circuit cogging torque is an issue. We've mentioned that before. This happens when the magnet sides line up with the slot sides in the stator, and there's a breakaway torque to get the rotor to move away from the detent reluctance torque position. This is periodically a function of the number of poles and slots. Its magnitude depends on the magnetic flux and the magnetic reluctance and the number of slot and magnet edges that line up. So you can reduce that significantly by adjusting the magnet arc angle slightly, for example, so that both sides don't line up with slot openings. Or you can skew or shape the poles and eliminate it almost completely, like we talked about in the last presentation. But you can calculate the Cogging torque using this this relationship here. Integrate the Maxwell stress tensor within the air gap. This requires a complex derivation of the air gap permeance from the slot geometry. So the best way to accurately predict this is using FEA solvers. You measure it with a torque watch, which we mentioned before. Here's a picture of the torque watches. I didn't have those in the last lecture, but they're here. The face of them looks like a little watch, and they have a little pointer on them with friction. So as you use this 3-jaw chuck to attach to the motor shaft, and then you rotate this by hand, and the peak torque it sees, that'll be the breakaway torque, will be held, or a position of where that reading was will be held with this friction pointer that's built in there. Honeywell make these, and a Japanese source, Tonichi, makes them, and they're very handy. They come in different sizes. They're small. They come with a 3-jaw chuck for easy assembly. Here's a list of the sizes that are available by Honeywell and Tonichi. Now the torque calculations for these machines, the K sub T is a result of the magnet flux linkage with the stator phase conductors, and we said how you calculate that, and the rotor flux, and those, the Z has to be corrected for the winding factors, but that's not a big deal. Therefore, the torque you get, this is a K sub T number, the torque you get requires current control, and so current is torque. Voltage is speed, current is torque. Current is controlled by the drive circuits from the inverter. Faraday's law says the rate of change of flux linkage equals the induced voltage, so that's certainly true. The turn times of flux gives you the voltage for with constant inductance. And this is very important for generators. The torque equations are given here for different motors. Now you'll notice there's a square wave motor has fewer. There's a formula for the square wave and the formula for the sine wave version here. Makes a big difference between the two. This takes into account what's outlined in Chapter 8 in our book about the relationship of the K sub T and the K sub E, so that the torque per amp takes into account the RMS sine wave in terms of the how it contributes to the flux linkage. The reluctance torque for the IPMs is very similar to the reluctance torque calculations in an RSM or a SRM, because this is a hybrid machine and it does have a reluctance torque, and the torque is determined by the flux linkage between the aligned and the unaligned position, or the D-axis and the Q-axis, and the co-energy in that energy conversion loop. If that's integrated, then you come up with the reluctance torque, which is plotted as a function of rotor angle, and to get the total torque of the machine, you add the magnet torque and the reluctance torque together at whatever angle you look at where the current vector is placed, and that gives you the total torque. This is a finite element analysis of a IPM. This happens to be the Toyota Prius motors. You see the pole mags can be multi-layered. This is a single layered magnet. and it's designed with saliency, and at some rated current here, we see some effects of saturation in the tapered teeth, and these webs that hold the rotor together are certainly saturated. As we've said before, the flux density is not uniform in all the teeth. It's high in some of them and almost non-existent in others. So that could mess up your loss calculations if you assume the same flux density in all the teeth, and you're going to misrepresent your losses. The alignment torque comes from the rotor magnet flux linkage in the direct axis, and the reluctance torque comes from the rotor saliency from the quadrature axis here, which are soft iron poles between the magnets. This is the torque equation for the sum of both of those. We looked at that before in the last configuration at the optimum gamma or phase angle. And that concludes this lecture. Thank you.